Good morning, everyone, and thank you for joining us for today's webinar. My name is Jean-Pierre Picard, and I'm Product Marketing Manager at CM Labs, and I'll be your host today. With me online is Marc-Alexandre Vezna, our Product Manager for Vortex Software Solution, who will be taking on live demonstrations during the session. We are going to get started with today's presentation, which is part of our Vortex University webinar series. If you're not familiar with Vortex University, it's a monthly simulation webinar series in which we tackle a specific Vortex topic and we go and do a deep dive on it. So this goes beyond what you'll see in our normal product release types webinars, and we try to go into more complex questions and topics. Now you can keep track of the upcoming sessions at the address listed on the screen right now. If you are getting started with Vortex or are not familiar with Vortex Software Solution, it is CM Labs' real-time visualization and simulation platform. It's used by companies across the globe for virtual prototyping, so that is creating virtual versions of machine designs to test their performance, but also for operator training and operational planning. Vortex is used in many vocational schools and in fleet operations across the globe to train new and experienced operators, but also to test the ability of equipment to perform specific tasks before a specific complex task, such as heavy lift scenarios. Now it's deployed worldwide and includes several modules to create and simulate ground vehicles and maritime vehicles. So today's presentation will be split in 3 sections. The first one will last 10 to 15 minutes, and it'll be an overview of the different troubleshooting tools available in the Vortex Editor. Then we'll move on to a second section where Marc-Alexandre will walk us through 3 troubleshooting scenarios from Vortex samples. So troubleshooting issues that you have to run through when preparing Vortex samples, and that'll give you a good idea of how we internally go about identifying the root cause of issues when we're working on simulations. Finally, we'll finish, as usual, with the live Q&A. If you have any questions during the presentation, you can send them using the questions box on the right-hand side of the GoToWebinar interface. If you have any issues with audio or visual, we'll be doing our best to help you troubleshoot it during the presentation. We've also made today's presentation available using the Handouts section. Now, we'll be sending a recorded version of today's webinar after the end of today's presentation, and it'll also be available on CM Labs Sales Portal for those of you who have an account. So if you have questions about a specific section or you want to get back to it, then you'll be able to do so. We're going to be using the Vortex Editor for today's webinar, which is about troubleshooting using the Vortex Editor. Now, if you're not familiar with the Vortex Editor, it's our desktop application that's used to create and validate mechanisms, scenes, complete simulations using your desktop. So you can use this to set up more complex simulator, but still have a desktop-based simulation environment. All right, so let's jump into it. So we're going to be showing you today how to the different tools available in the Vortex Editor, but also a bit about how we go troubleshooting simulations. But this is a complex topic because every simulation is different, and you're going to run into issues that aren't always exactly clear where their cause is. So I invite you to keep an eye out in the Vortex documentation. There is a fairly extensive troubleshooting and optimization section, which we'll retake some of the topics we have today, but also go into depth into some other types of issues that are either hard to cover in an hour session or that are maybe a bit more uncommon, but you might still be running into. Now, before we look at tools that are only for specifically for troubleshooting, I'd also like to come back on some manipulation shortcuts that are available in the Vortex Editor. Some of these might be familiar to you, some of these might be new, but they are especially useful when you're trying to get very precise control over the placement of objects, mechanisms in a scene that is causing you trouble. The first one is mouse spring. Mouse spring can be used using the Alt button and the left mouse button, and it allows you to apply a spring force on an object. That spring force will be based on the distance you drag it from the object. So as you can see on the video on the screen right now, you can move it just a little bit by using a small distance, or you can actually throw it around using a bigger distance. If you want more precise movement without applying an actual force on the object, then you're going to want to use Move Object, which is Alt, Shift, and the left mouse button. Now, using Move Object, you're going to be grabbing a part of the object and dragging the entire assembly around, and you can then either let it go from a certain height or deposit on the ground at a specific position. We also have the rotate object shortcut, which is Alt-Shift plus the middle mouse button. What this does, it allows you to rotate an object around its center, and this will not move the object. It will be pinned to its center of location. So that allows you to move it and look at how parts are attached under those types of movements. Of course, there's also the step-by-step simulation mode, which allows you to advance one time step at a time. And as you can see here, it's located on the right of the play simulation button. The way it works, I'm just going to start a short video here, is once you pause the simulation, you can press on the step-by-step simulation. It will advance one step at a time. Now, when you have issues with a simulation, very often it will happen in a few time steps. So this is especially important to be able to lock into the time where you see some issues arise. And you'll see in our troubleshooting case studies a bit later that this is something that is really important when you have issues with contacts, for example. Finally, there is also the freeze and unfreeze object shortcut, which is Alt and the middle mouse button. Now, this allows you to make an object either static or turn it from static to dynamic. And this is good when you have an object that you want to freeze, so that you can either focus on other parts of the simulation, or you want to be able to look at its state for throughout the simulation a bit longer. All right, so if we jump into troubleshooting specific tools in the Vortex Editor. So in the Vortex Editor, you're going to have 5 tools that are really for troubleshooting steps of simulation. So the Wireframe Display, the Inspector Panel, and the Debug Display, which are the 3 ones we'll be focusing on today. You also have the Graphics Debugger and the Profiler tools, but these are a bit more targeted towards optimization, which we'll cover in our next Vortex University webinar. They are fairly extensive tools, so we'll take a full hour to look at them. If you look at the Vortex Player, you also have tools there. You also have the Profiler available, which is by and large the same that you'll find in the Vortex Editor. And you also have a tool that is called the Debugger. Now, the Debugger is a way to access properties such as the one you'd find in the Vortex Editor while you're in the Vortex Player. We won't be looking at those specifically because they will mimic steps you take in the Vortex Editor, and anything you can do in the editor with those 2 tools will reflect itself to the Vortex Player. So what is Wireframe Mode? Wireframe Mode is a way to toggle the visualization mode of your scene from the full graphical display as we see right now to one that shows the vertices and triangulations of objects in that scene. When you press F2, it will move to a wireframe mode such as this, where you see all the vertices of objects. Now this is great because you get to actually see the penetration between objects without graphics blocking the way. You can also press F2 one more time to display the density of polygons with the point mode. So these modes toggle in from one to the other in a rotation. And you'll see later that the wireframe mode is great when you're looking at very small contacts, because these occur around the vertices usually. Next up is the Inspector Panel. The Inspector Panel is a tool that allows you to see information about the complexity of the object you've selected. That information will vary based on the type of entity you've selected. So if you're selecting an assembly, such as you see in the top, you're going to have information about its visuals, but you also have information about its mass, its number of parts, and constraints. If you were to select a graphics gallery, then you would focus specifically on the amount of memory it takes and the complexity of its visuals. You can open the Inspector Panel under the View menu option in the editor and then select Windows. So it's where you would go to turn on or off things such as the Explorer panel, the Properties panel, and that's where you'll find the Inspector Panel as well. The third tool that we're looking at today is the Debug Display. Now the Debug Display has a lot of information that can be made available through it. So we'll spend a bit more time looking at these details. But what it does in a nutshell is it turns on a graphical display of the different properties of an object. Now you can trigger those that graphical display for a single object or for a whole scene. And it will vary depending on which type of display you're turning on. So if we look at the video here and we turn on using the right mouse button, for example, the collision geometry of an object, it will turn it on for an entire simulation instantly. But if you were to turn on the constraint display, and we'll look at that in a moment, you would have to go in the Explorer tree and turn it on as well for individual constraints. And then as you turn them on, you will see that they will appear on our screen right here. So you see the constraints that you turn on appear on your simulation. You could also go deactivate the collision geometry of objects, of the different objects that you have, and turn them back on for single objects if you wanted to only see a few of them. So let's look at those different properties we can turn on and turn off using the debug display. The first one is Parse Origin. Now, the Parse Origin display shows you the position of a part's transform. Now, this is great when you're trying to troubleshoot a part that's not moving around the expected location that you have in mind, or that's not moving as you would expect. So, as an example, let's take a wheel. Now, when you import your model, your wheel transform could be set, your graphical transform could be set at the bottom of the wheel, and you could be putting the same location for your part transform. If you were to set a constraint on that wheel and not to offset that constraint, then as you start your simulation, you notice that your wheel would turn around this this location, so just like my mouse is going right now. So as you turn it on, you'll see that your wheel is not moving right. You could look at the Parse Origin, figure out that, okay, I need either an offset constraint or I need to move my transform location. And that provides you with the knowledge you need to figure out the proper way to fix your issue. So a center transform like this, then if we had our constraints set to the transform location, it would work as expected and rotate around its center. The second and third checkboxes allow you to display a part's center of mass and its inertia tensor, and those two work very closely together. It's useful when you troubleshoot an object that either leans, tilts, or slides in ways you wouldn't be expecting in real life. Now, a good example of this would be for a auto-computed inertia tensor for our forklift. If we use the auto-computed option, then you'll see that its mass is actually spread evenly across its graphical elements, and its center of mass is actually in the cabin here. If you were to drive this forklift around, if you hit anything that was located at the upper portion of the forklift, it would tilt very easily and it would not react normally. It would look very unnatural. If you look at a proper inertia tensor and center of mass, it would be much closer to the ground because you have a very heavy engine here, whereas the upper portion is mostly empty space where you have the cabin. So if you were to be fixing your tilting and leaning, then you'd have to bring back the weight center of mass to the bottom here. Next up are attachments and attachment points displays. Now, if you turn these on, you'll be able to see all of the mechanism's attachment points and as well the location of active attachments and if they have been offset. So what we see here is our ROV sample. And the ROV sample has a lot of attachment points because it's designed in a modular way that it can use different types of accessories like grabber tools, torque tools, and such. Because of this, there's a lot of attachment points, and sometimes if you have a tool attached to it, you could be attaching it to the wrong location by mistake. Now, if you have active attachments, then you will see them displayed with a line that will show its attachment location. So in this case, our two attachments are attached to the bottom of the excavator and in its center. They are offset to the other edge of the line. So you can see that the cabin is an attachment, and we've offset it in one direction. The other attachment we have here is actually a sound generator extension, and it generates the engine noise. So it was offset to be located at the same location as the actual engine on the excavator. This is useful when you're troubleshooting either an attachment that is not, that doesn't have the movement that you'd be expecting, or that is simply not following your mechanism. Next up is contacts, and the contacts display is actually one of the more complex tools in the Vortex Editor troubleshooting portfolio. What it does, it displays contacts in an active simulation, all of them. But it actually has multiple visualization modes that you can activate with Alt-C. So the first one, the default one you turn it on is contact normal. And it's going to display the normal of contacts in the scene. So as you see on the forklift here, it's resting on the ground, and the normal is actually located perpendicular to the ground. If we toggle to the next, contacts force, we'll see the force and the direction of the different contacts in our scene. So the blue line here tells us that the direction of the force applied is towards the left. We can also turn on contact torque the visualization mode, which tells us the point of that torque is applied and the direction and strength of it. Contact penetration is a trickier display. It shows you penetration in the simulation. So we've bumped it up here for this example, but typically penetrations will be very small. So this is a extended line, so we could clearly see the strength of those penetration contacts. And finally, contact direction will tell you the direction of your contacts. There's an extra layer of complexity here, and that is especially for color contact normals. So I'll just let Marc-Alexandre walk us through the different color coding for contact normals.
Thank you, GP. So basically, the contact normal is a color-coded system between match and not match contact. So a match contact is a contact that was present in the previous step at the same location, but also a contact that has the integral slip displacement option enabled. What this does is that it adds a spring to simulate the friction effect. So basically, if you have a box on a shallow slope and you don't want it to slide off, you're going to enable that option. It's fairly costly in terms of simulation, so we try to avoid it when we don't need it, but you need it for preventing sliding. And sliding and not sliding, basically, you can think of them as sliding being dynamic static, and not sliding being dynamic friction, and not sliding being static friction. In a not match contact, which means that it's a new contact, for example, the corner of a box that's falling, that's touching the ground for the first time. If it's a static contact, it's going to be magenta. If it's a dynamic contact, for example, if there's a sideways motion to the box as it hits the ground, the contact is going to be displayed as red. The color will change and flicker depending on the type of contact. It's possible that it changes throughout the simulation, but it's useful to know what's going on. You can also see the line better by using Alt plus X and Alt plus Z to increase and reduce the length of the line, so you can see them better. For example, the penetration line that GP was showing just a moment ago in the forklift, we used Alt Z to increase the length to see them better.
Thank you, Marc-Alexandre. All right, so the next display mode is constraints. And what it does, it displays activated constraint and it displays their axes and limits. Now, you have to go and activate individual constraints as we've seen in our video earlier, and they will not all show automatically. And the display is based on the constraints type. So if you were to have, for example, an inch constraint like the one we have on the wheel here, you're going to see its center, the way it will rotate, and its different axes. If you add a prismatic constraint, like the one we have on our forklift palette here, then you will see the extent to which it can move and its location. And you would have a similar display for a cylindrical constraint with the addition of its axis of rotation. Now you have to go and turn these on in the Explorer panel for the constraints you wish to see, but you can turn on all the constraints under a specific section by using their grouping constraint. All right, the next one is collision geometries, and what this does is it displays a gray-white overlay for the collision geometries of your model. Now, this is good to see where the collision volume and the graphical model are not matched. So if we look at our LAV here, for example, we can see that we have on the turret, we have some elements that are sticking out above the turret. But if we look at the contact volume, the collision volume, then you'll see that this is actually not part of the collision geometries. Now this could be because we wanted to save some processing and limit the complexity of the volume, or it could be an oversight. The net result, though, is that if we were to drive this in a narrow space and we expected this part to collide and it did not collide, it's because there is a difference between our collision volume and our graphical model. So this is good to turn on when you're trying to troubleshoot either a contact that's happening too fast or too late or not happening at all. So you can see those collisions within a mechanism as well, and you can then define the the collision rules that you need to add to your mechanism. If we go back to our example of the forklift, for example, we could, and we made a collision volume for our cabin, then the wheels are actually kind of recessed in that cabin. And if we make a simple prism for the cabin, then they would actually collide together unless you put in a collision detection rule, which is something that you could forget about when you're working on a lot of mechanism at the same time. It also allows you, using collision geometries, it also allows you to see how two objects collide, how deep they actually penetrate, because you'll get to see the difference between the model and the collision volume itself. All right, next up is accessories. So turning on the accessory display allows you to see additional information about extensions. Now, the information you're going to be seeing will vary based on the extension. You could see, for example, such as on the screenshot here, light sources, sound sources, but also camera positions, and these are things that aren't physically part of your simulation. They're basically there as extensions. But you can also turn it on for earthwork zone to see the soil density. You could also see cable waypoints on your cable by turning it on your cable system. Finally, the last option, the debug display, is a graphic node origin, and what it does is it shows the position of the graphics nodes transform. So that's useful when you're trying to troubleshoot a graphic node that is not moving with its associated part. Sometimes you're going to have transforms that are set differently or that are not properly attached. All right, so we're going to jump into the meat of today's presentation. We're going to go into 3 troubleshooting case studies with Marc-Alexandre. The first one is what we call the case of the bouncing forklift. Now, this one, I believe, we encountered when you were working on the 6.7 warehouse sample, Marc-Alexandre, which was being remade from scratch. And as you can see in the video here, there was a periodic unexpected bounce when driving over sections of what is supposed to be a flat warehouse floor. So I'll pass the controls to Marc-Alexandre, who will be able to show us this issue in action. Marc-Alexandre, it's all yours.
Thank you, GP. So this is the forklift in the warehouse. Everything looks fine, so I just lift off my mast and I start driving forward. And, oh, what's this? There's sort of a bump in the when I go over a line in the ground. I'm not sure what's going on. So what I'm going to do is that the first thing is that I'm going to check my collision geometry to see if I made a mistake somewhere. So I right-click on my debug display and I see that my geometry are enabled. So I can go into my Explorer and I select Geometry, and now I can see the collision geometry of my forklift. Well, the wheels look fine. I mean, there's no bump. It's a nice cylinder, so it can be that. So I'm going to close that. I'm going to go back into Static Object, and we're going to check out this time the ground itself. So the ground looks fine, but oh, wait a second. What's this? There's sort of a line there. And it seems that, yep, that's where we get our bump. Okay, so at least now we have a direction where we can go. So we're going to turn off the geometry again. And this time I'm going to use Shift-C. Sorry about that. Click in the viewpoint. There we go. Shift-C to display our contact in the scene. So you can see that the box have integral slip displacement enabled because we don't want the box sliding around if we have a slope. Right now the warehouse doesn't have one, but eventually we're going to want to add a concrete ramp, and it wouldn't be good if the boxes were sliding down the ramp as we deposit them at this location. You'll also notice that some of the lines are blue. What blue means is that there's actually a contact, but it's negligible. It's 0.00001 Newton, if I remember correctly. In this case, the box has 3 runner at the bottom, and that's why we're having most of the weight on these 3 points. And you can see that the other points are not doing so a lot of effort. Let's get back to our forklift. So we're going to move forward a bit, and whoa, you can see that there's a lot of action going there. See, we have multiple contact when we go over that spot in the ground, and that creates a jiggling effect in the motion. So to figure out what's going on, we're going to go in the viewport and we're going to go to F2, and we switch to wireframe mode. So we're going to still move the forklift forward, and we realize that whenever we cross that line, we're having multiple contact. And if we zoom in like this, we realize that there's actually multiple triangles on the ground at that location. And then you realize that the artist tried to create concrete blocks to accurately simulate the expansion joints in the warehouse, in the ground of the warehouse. Now, this is nice, but it's giving us a lot of problem in terms of contact. How can we fix this? Well, there are several ways we can go about it. The first one is the easiest, is go back to the artist and ask them to remove the expansion joint and just create a flat surface. The second option is to use the various CAD import tools in the graphic gallery and try to repair the polygon yourself. It's not always going to work, but sometimes it's a quick and easy solution. The third solution that we could try is, instead of having the warehouse as a terrain, to take the graphic gallery of the warehouse ground and make it into a mechanism which is set to static, and then we can just create a box collision geometry for the entire floor, and that's going to avoid the problem as well. If you want to keep the expansion joint because you think that the motion of the bump as you go over it is important to the driver experience, there is a final way to do it. What you can do is go into the material table and change the property of the contact between the wheel and the ground, change the damping or the stiffness or the friction in order to get a better contact that will avoid having this huge bump as you go over the line. Back to you, GP.
Thank you, Marc-Alexandre. So that was our first scenario where we had an issue that we used in the troubleshooting tools. The next one was goes back a bit further to the Vortex 6.6 Forestry example. Those of you who have been using Vortex software solution for a while will remember that in 6.6 we added a new forwarder and a new sample that featured a lot of speed-tree materials and a very uneven terrain. Now, some of the issues that came up were specifically related to logs, which were either bouncing wildly or falling through the terrain in some cases, and this one required some investigation. So I'm just going to switch this back to Marc-Alexandre, who is now on the proper version. So Marc-Alexandre, you have the controls.
Thank you, GP. So I've launched the forward scene, and as you can see, my log is it's shaking. It's wildly dancing, some of them more than others. This one is sliding a bit, where my forwarder is completely stable. So we're going to try and figure out what's going on. I'm going to use Shift-C again to see the contact. So you can see that the forwarder is stable. There's no problem there. But we're seeing a lot of varying contact in the logs as they touch the ground. And while I'm here, I'm just going to show you a quick trick that we use in the forwarder example. If I just pivot down here, you'll notice that the collision geometry is here, and there's a graphic layer just above it. And that's because we use a second graphic gallery to create the ground cover, which would be moss and other soft vegetation. So that way the logs and the vehicle sync correctly into the terrain. But this shouldn't affect our contact because we're just interested in what's going on with the collision geometry of the ground. So let's say we take this trunk and we highlight this collision geometry. Well, we can see a problem right there is that we used a convex shape to follow the irregular tree trunk, and try to get as much detail of the bark as possible. This means that there's not a flat surface on the bottom. So whenever it tries to get equilibrium, it can't because it's constantly flipping from one contact point to the other. So it goes on one side and then back to the other, and then it keeps rolling that way. So that's not great for us. So there's a couple of ways we can fix that. The first one would be to, for example, change the collision geometry of the log to something that's more cylindrical. It's going to roll, and it's not going to be very accurate in terms of gripping. So it's a poor solution, but it would work in case of bulk material management where it's not really important to get great contacts, for example. The second way we can work on this is to go into our material table, get our log and ground contact, and start playing around with the damping, the stiffness again, and changing the friction scale, and try and get the log to have a little more softness in its contact with the ground, in the hope of absorbing some of the motion. You'll notice that the slip displacement is set to on. This is to avoid having the log slipped a lot on the slope. This one is still slipping because this is supposed to be mud, so it's sliding quite a bit. So we've played around with this, and we had some success. I'll show the result in a few seconds, but it wasn't great. The logs were still somewhat moving, so if you can see that log, it's sort of stable but still sliding, and it's not something that we think is great for the simulation. There is another option that we can try, and that's to go into the assembly of the trunk itself. So I'm not going to open the assembly to save time, but if you select the part, there's a section in the dynamic tab here that's called auto sleep. And auto sleeps are a set of threshold that if the object goes under these threshold, it goes to sleep. What this means is that the simulation ignores it for a while. So it becomes static, it doesn't move, nothing happens to it until you bother it again. So what we're going to do is that we're going to go see another log here that had its properties changed, and you can see that this one is stable because we've changed the contact property, and also we've made it we've changed the auto sleep on it. And just to show you something else, so we're going to click on the center of mass and the inertia, so you can see that the inertia tensor is correct for the log, and the center of mass, you can see it as a purple dot here in the middle. It rescales itself, so I can't really get too close, but you can see the purple dot, and what purple means is that the part is asleep. So I'm going to use Alt and left mouse button, which is the spring that GP showed us earlier, and I'm going to roll the log a bit, and you'll notice that it's now blue because the log is active, and then it stops rolling and it goes back to sleep and it turns back to purple, and now my log is asleep again. If I lift the log, you can see that it goes back to blue, and then once it's stable, it stops moving. So whenever you have something that's moving wildly and you can see that the contacts are not regular, check your friction, your contact property. And in last resort, you can play around with the auto sleep coefficient here, the values, in order to get something that's a lot more stable. Back to you, GP.
Thank you, Marc-Alexandre. So that was our second case study. For the next one, we're actually not going to be using an existing sample. It's coming from a test we were doing related to a vehicle retrieval scenario. And the issue we ran into was, and as you can see on the screen here, was a shackle that was hovering away from the vehicle during the vehicle redress phase. Now, as you'll see once it's in action, it's actually quite peculiar seeing it happen like this, because it's still applying force on the vehicle being redressed. So, Marc-Alexandre, I will pass you back the controls so you can show us this in action.
Thank you, GP. So basically, this is our test scene. So we have an engineering vehicle over there, and we have our damaged vehicle over here, and there's a cable with a pulley here. And because this is a recovery scenario, we modeled the shackles and the pin separately from the vehicle. Normally, for efficiency purposes, what you would do is that you would take the end of the cable and you would attach it directly to the part of the vehicle without going through an attachment point or a shackle or anything like that. But in this particular case, it was important for the test to have the ability to move the cable to different section of the vehicle and have the shackles move, because this changes the way the force is applied. So for this case, I've to demonstrate the problem more clearly, I've set up a kind of an impossible situation. I've wedged the damage LAV between a rock and a hard place, and so when I pull on it with the engineering vehicle, the cable is going to be under a very high amount of stress. So the first thing I do is that I've preset my cable already, so I just activated the cable and it creates a cable between the winch and the pulley. Then I'm going to go to my winch control and I'm going to start reeling it in. So the cable lifts and we keep going, and then there's tension being applied to the vehicle. Now keep in mind this is a 15-ton tank and it's being pulled by a static vehicle here. So we keep pulling, and there's more tension being put on the cable. Now I didn't enable the braking feature on the cable, so there's no place where the energy can go. So you can see that the shackle is starting to oscillate wildly. So I'm going to pause the simulation here, and oops, you can see that the shackle is completely detached from the vehicle and the cable itself. So what's going on here? So the first thing you're going to want to do is check your cable property. So if you check in the dynamic cable, you have to make sure that your physical property are correct for the cable that you want to do. Whenever you see a cable oscillate wildly or detach itself like this from the vehicle, it usually means that there's too much energy in the system. But since we didn't enable the breakage parameter, the energy has nowhere to go, so the cable oscillates wildly until the simulation crashes. So it's very important to make sure that you have your physical property correct, and you also have the breakable factor here set correctly as well if you want it to have a realistic outcome. Now, this is going to lead to some interesting effect. When I first set up this scenario, I remembered that I had the wrong type of cable. So basically every time I pulled on the tank, the cable would break, and I didn't understand what was going on until I went back and I checked my physical parameter and I realized I was using a cable that was way too small for the 15-ton of the tank. So that breakage was actually an emergent property that was telling me, hey, that cable is just too small. And that was perfect for the scenario, because if the soldier chooses the wrong size of cable, that's exactly what's going to happen in real life. So that was the first step. So I checked, and our cable is correct, so that's not that. Next, we're going to go into our damage LAV here, and we're going to open up the assembly, and we're going to go and check the constraint where the loop attaches to the vehicle, and then we're going to check also the part origin. So we can see that the hinge where the pin of the shackle is correct. It's placed at the right section. The origin of the part is correct, and the location of the constraint here is correct as well. And yet this is still detached. So we know that there's a problem elsewhere. We set up our constraint correctly. We set up our cable correctly. What else could it be? So we're going to look into our part itself, and we're going to start checking its parameters. So, oh, there we go. So we can see that the mass is the default mass of 1 kilogram. Now, a real-world shackle might not be much heavier than 1 kilogram. It might be 5-6 kilogram. But in this case, it's attached to a 15-ton tank, so 15,000 kilogram. Now, the solver that Vortex uses has a time step of 1/60th of a second. So we're doing 60 steps per second. In that amount of time, there's a finite amount of calculation that we can do. And if the mass ratio are too big, that is, if the one part is too small compared to the other, we're going to see some very weird effect, which is what we're seeing right now. So the solution in this case is just to simply increase the mass of the part, so the shackle and the pin itself, incrementally until we get a stable simulation where the cable doesn't detach from the vehicle, and the vehicle can actually be flipped back on its wheel. So when I created the scenario, obviously we didn't have this rock here to block the way, so I just simply increased the mass of the shackle until I got a stable simulation. Back to you, GP.
Thank you, Marc-Alexandre. So hopefully these three examples show you a bit how we go about when we figure out something is not going as expected in simulation. Now, all of these have very different causes and solutions, but they all start with more in-depth look at exactly what's happening at a precise location of the issue, using the different tools to really isolate the possible cause. So, as I mentioned, every simulation is unique. So troubleshooting a simulation is going to be a challenging step that will be unique for every simulation. What the Vortex Editor gives you is it provides you with an extensive set of tools to go around the different root causes and be able to figure it out and then fix it efficiently. Again, I invite you, if you have interest regarding some of these tools, to go into the Vortex user documentation, which goes into extensive details about specific types of scenarios you might encounter as well. Of course, we're here to take live questions now as we're going to our Q&A section. And you can also download today's presentation materials in the handout module on the right-hand side interface. We expect today's Q&A to focus on some fairly specific issues going on. So if you have issues with a specific simulation, send your questions our way. We'll take them privately, obviously. And for those of you that will be leaving us, we'd like to invite you to next month's webinar, which will be held on October 20th. And it will be about the second part of our troubleshooting webinar series. And we'll focus on optimization of simulations. So once they work as expected from a dynamics perspective, how do you make sure that they run smoothly and at your target performance? So again, thank you for those of you who will be leaving us. Thank you for joining us today, and we'll now be going to questions.